Hey everyone, welcome back. This is lesson 8.4, rational functions. The objectives for today, you're going to be able to graph rational functions. You're also going to be able to transform rational functions by changing the parameters. Your vocabulary for today is rational function, discontinuous function, continuous function, and whole in a graph. All right, a rational function is a function whose rule can be written as a ratio of two polynomials. There's where you get the word rational. It's a ratio, actually, so that will help you remember what a rational number is. It's a number written as a ratio of two polynomials. The parent rational function is f of x equals 1 over x. Its graph is a hyperbola, which has two separate branches, and you'll learn more about the hyperbolas in chapter 10. All right, so before we go on, I just want to review what is an asymptote. All right, so an asymptote is a line that a graph approaches as it moves away from the origin. Asymptotes can be vertical or horizontal. Vertical asymptotes cannot ever be crossed, but horizontal ones can. Vertical asymptotes are determined by the zeros of the denominator, which is what we've been trying to find so far, is when is the equation undefined. All right, and horizontal asymptotes are determined by comparing the degree of the numerator versus the denominator, and we're going to learn more about that today's lesson. All right, like logarithmic and exponential functions, rational functions may have asymptotes. The function f of x equals 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. A rational function, f of x equals 1 over x, can be transformed by using methods similar to those used to transform other types of functions. So some of the same rules are going to apply. All right, so this is our basic function, and let me just compare it to our parent function again. The parent function is f of x equals 1 over x. So let's talk about this first a here, all right? So if you think about it, if we multiply 3 by this entire function, basically we're just doing a vertical stretch, and 3 times 1 would be 3. So this a tells us whether it's a stretch or a compression. It's just a number that's multiplied by the parent function, but it goes right over here because 1 times anything. All right, and just like before, if we add something to the end, which we're going to call k, it's going to just be a vertical translation up or down depending on whether it's positive or negative. And then in the denominator, we have this h here, all right? And the h is the horizontal translation left or right. And it's just like thinking about it being snuggled up with our x here. So anything that's, even though it's not going to actually be snuggled up like we're used to seeing, you can think of it as snuggled up. And so that h is going to tell us about the horizontal translation, whether it's left or right. Okay, so our first example is transforming rational functions. I know that's your favorite thing to do. So we're going to take the graph of f of x equals 1 over x as a guide, and then describe the transformations and graph each function. So looking at a, it says g of x is going to be 1 over x plus 2. So as you notice, we have this 2 snuggled up right here with our x. So because of that, we're going to actually translate 2 units to the left, because remember, horizontal is horrible, and so we almost always do opposite of what it says. So if it says plus 2, we're going to think that it's going to move 2 units to the left. So here is our function f of x, and in order to translate it 2 units to the left, we just pick it up and move it over 2 units to the left. All right, next, in this next one, we see that we're going to take what's our y, because notice f of x equals 1 over x. That was just our y. And we're just going to add a minus 3 to it. So we're actually going to subtract. So that's vertical. So that tells us we're going to just go 3 units down. So here is f of x right here. And then we're going to translate it 3 units down. And there it goes, 3 units down. Now, I do want to take note of the asymptotes here. On A, notice that my asymptote before was right here. And when we shifted the graph over 2 units to the left, my new asymptote is right here, 2 units to the left. And same with the vertical. My original asymptote was here at y equals 0. But then when I translated it 3 units down, notice that my asymptote moved 3 units down too. Okay, so you try one on your own now. So you're going to use the graph f of x equals 1 over x as a guide, and then describe what happens, and then make a graph of it. Okay, so when we look at this, we notice that what has happened is my x has got a 4 added to it now. So all that tells me is I'm just going to translate my graph 4 units to the left. So don't forget, plus horizontal is horrible. So if it says plus, we're going to actually be going to the left. Okay, so now to go ahead and graph. This first graph that I have here is the graph of 1 over x by itself, and then all we have to do to translate it is we just move our graph over 4 units to the left. And notice that my asymptote also moved 4 units over to the left also. So my new asymptote is right here. All right, and then same with the second one. Notice that this is my original function, and all I've done is added 1 to it. So that should be relatively obvious to you. That's a vertical translation, 1 unit up. So here is f of x equals 1 over x. And then to move it 1 unit up, we simply just move it 1 unit up. And that's all there is to it. And now notice this time my asymptote did not change at all. It stayed the exact same place. Okay, next. The values of h and k affect the location of the asymptotes and the domain and the range of rational functions whose graphs are hyperbolas. All right, so here's an important chart for you to keep in mind. For a rational function of the form f of x equals a over x minus h plus k, the graph is a hyperbola. There is a vertical asymptote at the line x equals h, and the domain is x such that x is everything but h. It can't be h. And there is a horizontal asymptote at the line y equals k. And the range is y equals y such that y cannot equal k. So we're going to do some problems like this to give you a better understanding of it. But I guess the main thing I just want to remind you of is that the horizontal asymptote is actually up here. This is going to tell us our horizontal asymptote. It's the actually translates things in the vertical, but that will tell us what our horizontal asymptote is. And then the h is going to tell us what our vertical asymptote is. Okay, so don't think h is for horizontal, although it seems like that would be a good idea. H is actually going to be for vertical, and then the k will tell us about the horizontal. All right, let's take a look at this example. We're going to identify the asymptotes, the domain, and range of this function. All right, so just taking a quick glance at it, you should notice right away that there's a 3 added to our x. So that tells us that this whole graph is going to shift 3 units to the left, all right? And we also see this minus 2, so that tells me that the whole graph is going to shift 2 units down. All right, so the first thing that we're going to notice is our h and k. Now our h is this 3, and notice that it says h is negative 3, but when we look at it, it says 3. Well, remember, we're moving to the left 3, and also if you remember back to our formula, it said a over x minus h, okay, and then plus the k. So that minus, in this, if it's going to end up being a positive 3, this would have to be a negative 3. All right, but I don't really worry about that so much as I just say what number is going to make this 0, and that's negative 3 would make the bottom 0. So that's all I do to think about it. I try not to get too wrapped up into this formula over here. All right, and in addition to that, we need to notice that our k is negative 2. All right, so once we know that, we can notice that the value of h is negative 3. So h tells us, remember, not horizontal asymptote, but it tells us the vertical asymptote, okay? So we're going to have a vertical asymptote at x equals negative 3, all right? And the domain then would be everything except x equals -3. X such that x is not equal to -3, but everything else will be included in it. So this is how you'll need to write it. So get in the habit of taking a look at that. All right. The next thing we're going to do is talk about the value of k. All right, so if h is the vertical asymptote, and we know that k equals -2, that's going to tell us about our horizontal asymptote. So it tells us that our horizontal asymptote is y equals -2. All right, so horizontal is y equals -2, so now we need to talk about the domain, or I'm sorry, the range. And the range is y is such that y is not equal to -2. It's not too complicated on that one. All right, and you can check this to make sure you're right. Graph the function on a graphing calculator. And the graph suggests that the function has asymptotes at x equals -3 and y equals -2. All right, and here's what a picture of this would kind of look like. You can see it looks like there might be an asymptote right about here, and also one right in here. Okay, so that's where our asymptotes are. All right, so try this one on your own. Turn your video off and give it a try. All right, on this one, we're to identify the asymptotes. So let's take a look at our graph. Let's think about what happens first and then identify things in it. Notice it says x -3, so that's going to tell us that there's a horizontal shift, but it's actually going to go to the right. So our x is actually going to be +3. And I, again, just think about what is going to make this 0, +3. All right, and I notice that there's a -5. That's going to be my k, and that tells me that my whole graph is going to go down 5 units. All right, so now that we have that, the first thing that we really want to do is just go ahead and identify our h and k. And so our h is going to be 3, and our k is going to be -5. All right, so once we know that, we're going to talk about our h first. Remember, h tells me vertical. H does not tell me horizontal, even though we'd like to think that. H tells me the vertical. Okay, and notice how I went ahead and I had already written up here x equals 3. That's going to help you remember. So the vertical asymptote is x equals 3. All right, next we need to talk about the domain. And if x equals 3 and it's an asymptote, that means that the graph is never going to reach 3. So when x equals -3, we're just going to have an asymptote, but everything else, the domain is all the x's except x equals 3. All right, next we look at our value for k, which is -5, and so that tells us we have a horizontal asymptote at y equals -5. And our range then is going to be y such that y cannot be -5. It'll be everything else, just not -5. All right, and once again, we can graph in your calculator the function on a graphing calculator. The graph suggests that the function has asymptotes at x equals 3. So here's x equals 3. And at y equals -5. So here's our y equals -5, and it looks like those could possibly be the asymptotes. All right, a discontinuous function is a function whose graph has one or more gaps or breaks. The hyperbola graphed in example 2 and many other rational functions are discontinuous functions. A continuous function is a function whose graph has no gaps or breaks. The functions you have studied before this, including linear, quadratic, polynomial, exponential, and logarithmic functions, are continuous functions. So now we're going to move on to the discontinuous functions. The graph of some rational functions are not hyperbolas. So consider the rational function f of x equals x minus 3 times x plus 2 over x plus 1 and its graph. All right, so here's its graph, and take a look at it. The numerator of this function is 0 when x equals 3 or x equals -2. Therefore, the function has x-intercepts at -2 and 3. The denominator of this function is 0 when x equals -1. As a result, the graph of the function has a vertical asymptote at the line x equals -1. All right, so I hope you were able to follow that. And notice that this graph, there's actually two parts of it, but they're discontinuous. They don't actually touch, like in the past when we had a quadratic equation with a parabola or even just a line or something continuous. But notice our graph now is not continuous. It's not one full piece, it's two pieces, and it could be many more. All right, zeros and vertical asymptotes. If f of x equals p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1, then the function f has two things: zeros at each real value of x for which p of x equals 0, and a vertical asymptote at each real value of x for which p of x equals 0. All right, now I know that doesn't really mean a lot to you yet, so let's do some more problems with it. Here's another page just kind of saying the same thing. So there will be a vertical asymptote at any illegal x. So that means when we have an x in our denominator, all right? So anywhere that would make the denominator equal 0. All right, so let's set the bottom equal to 0 and factor to solve to find where the vertical asymptotes should be. So when we actually have this factored out, which is x minus 1, x plus 1, we see that there are vertical asymptotes at x equal 4 and x equal negative 1. So this is where our vertical asymptotes will be depending on where x equals. So we spent the whole last lesson talking about when the equation would be undefined, and we would say x equals net 4. And so now we know that that's important to know because that tells us where our asymptotes are. Okay, so let's try an example working with these. It says to identify the zeros and the vertical asymptotes of this function. All right, so the first thing we want to do is find the zeros and vertical asymptotes. So what we need to do is factor the numerator. Now remember, to factor our numerator, we're going to have to find two numbers that multiply together to get negative 4, add together to get 3. Well, I think that would be positive 4 times a negative 1. There we go. So we could put that into the factored form, x plus 4, x minus 1 over x plus 3. So once we have factored the numerator, the next thing we look at is that, notice that the numerator is 0 when x equals negative 4. Okay, so if that was negative 4, it would equal 0, or when x equals 1. All right, so our zeros are at negative 4 and 1. Now, the next thing we want to look at is our denominator. The denominator is 0 when x equals negative 3. Okay, so we have a vertical asymptote at x equals negative 3. All right, so continuing on, here's our function some more. The next thing we're supposed to do is graph it. So in order to graph it, you can plot the zeros and draw the asymptotes, then make a table of values to fill in the missing points. And I'm okay if you just look this up on your calculator, but you need to be pretty accurate on your graphs when you draw them. All right, so if you were to choose some points, you could know that your asymptote is at 3, negative 3, and then just choose a few points in here to plot them. So once you do that, you would get a graph that looks similar to this. The main thing I want you to take note of is where the vertical asymptote is, which is at x equals negative 3, and we got that one right here with this. All right, so try this one on your own. Turn your video off and see how you do. Okay, again, we're to identify the zeros and the vertical asymptotes of this function. So the first thing that we want to do is find the zeros, and the way we do that is by factoring the numerator. So when we factor the numerator, remember we have to find two numbers that multiply together to get 6, add together to get 7, and that's an easy one, 6 times 1. So the factored function is going to be x plus 6 times x plus 1 over x plus 3. All right, the next thing we want to do is go ahead and notice that in the numerator is 0 when x equals negative 6 or x equals negative 1. All right, so that just tells us that there are zeros at negative 6 and negative 1. All right, when we look at the denominator, we see that when x is -3, then the denominator is 0, and we talked about that being undefined, and now we know that that tells us that there is a vertical asymptote at x equals -3. Okay, again, we need to graph this also, and I'm fine with you just putting it in your calculator. You can plot zeros, but the main thing I need to see on your paper is that you know where this asymptote is. This asymptote is going to be at x equals -3. All right, and so here you can see at x equals -3. You will need to be able to show me a few plots, a few points on your graph, and then have it drawn out like that. All right, and the main thing I want you to be able to point out to me is the vertical asymptote is at x equals -3. And that's just a chart. All right, some rational functions, including those whose graphs are hyperbolas, have a horizontal asymptote. The existence and location of a horizontal asymptote depends on the degrees of the polynomials that make up the rational function. Note that the graph of a rational function can sometimes cross a horizontal asymptote. However, the graph will approach the asymptote when the absolute value of x is large. And we'll go over problems like this so you can understand what we're talking about. All right, here's a chart to help you find the horizontal asymptotes. All right, so if you have a function, let f of x equal p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1. The graph of f has at most one horizontal asymptote. So here's how we find the horizontal asymptote. If the degree of p is greater than the degree of q, there is no horizontal asymptote, okay, none. If the degree of p is less than the degree of q, the horizontal asymptote is the line y equals 0, which would be just on our coordinate plane, just that y equals 0 at the axis. All right, so if the degree of p is equal to the degree of q, the horizontal asymptote is the line where y is equal to the division of the leading coefficient of p over the leading coefficient of q. So that ratio between the two is what your line is going to be. All right, so let's take a look at this. Here's another way of saying it. The leading coefficient is the number in front of the highest powered x term. So in our sample here, the degree of top is equal to 2, all right? And the degree on the bottom is also equal to 2. So the rule says that if the degree of the numerator is equal to the degree of the denominator, then there is a horizontal asymptote at y equals the leading coefficient of the top part divided by the leading coefficient of the bottom. So here's this example. Notice that I had a 2 and a 1. So the asymptote is going to be at y equals 2 over 1, or simply y equals 2 when you divide that out. All right, so here's where my horizontal asymptote is going to be for this particular problem. All right, so here's a summary one more time. I know I'm telling it to you a lot, and I have another page too, but it's really important that you learn this, okay? Vertical asymptotes are the values that are not in the domain. To find them, set the denominator equal to 0 and solve. All right, so that's easy. The vertical asymptotes are easy. Horizontal is horrible as usual, so shouldn't surprise us. To determine the horizontal or slant asymptotes, compare the degrees of the numerator and the denominator. If the degree of the top is less than the bottom, the horizontal asymptote along the x-axis or y equals 0. That's where our horizontal asymptote is. If the degree of the top is equal to the bottom, the horizontal asymptote at y equals the leading coefficient of the top over the leading coefficient of the bottom. And finally, if the degree of the top is greater than the bottom, the slant asymptote is found by long division, and we're not going to do that in this lesson. And one more time, this is the chart that I'm going to have you use, and you can just look at it one more time. It's saying the exact same thing. I think this one is probably the most simple way of looking at it. All right, so let's put it into practice here. So for this example, we're going to graph rational functions with vertical and horizontal asymptotes. We need to identify the zeros and the asymptotes of the function, then graph. So let's take a look. The first thing we want to do when we take a look at this is factor the numerator. So remember, in order to factor our numerator, we're going to look and say what two numbers multiply together to get -4, add together to get -3, and that's going to be -4 times 1. So our factors is x minus 4 times x plus 1 over x. All right, so now we can see in the numerator, it's 0 when x equals 4 or x equals -1. So if x is 4, this would be 0. If x is -1, this would be 0. All right, so the zeros are at 4 and -1. Now, the next part we need to do is look at the denominator and see when it equals 0. All right, and the denominator is 0 when x equals 0. All right, so that tells us that we have a vertical asymptote at x equals 0. All right, now the next thing we need to do is determine the horizontal asymptote. So now we're going to use our little chart here. So when we take a look at our chart, we look at the degree the highest degree of our numerator and the highest degree of our denominator. So the highest degree is 2. And the highest degree on the bottom is just 1. So when I look up here, I see that n, the number in the n value, is actually greater than m. So we're going to come down here and we see n is greater than m. So that tells us there is no horizontal asymptotes. There is a slant diagonal or an oblique, but we're not going to worry about that right now, but there's no horizontal. All right, so as are noted, the horizontal asymptote is none. All right, in this same example, we're going to just take a look at the graph with the calculator and using the table of values. When you put your graph into your calculator, you could put it into the y equals on your calculator, and you will see that there's actually a vertical asymptote at x equals 0, just like we predicted. All right, again, here's another example. Same thing, we're going to identify the zeros and asymptotes of the function. So the very first thing we want to do is factor the denominator because the numerator's already been factored. So I notice that this is the difference of two perfect squares. So that tells me that the factored out form of this would be x minus 2 on the top and x minus 1 plus times, x plus 1 in the denominator. All right, so next we're going to look at the numerator, and when the x equals +2, then the numerator is 0. So that tells me that the 0 is at 2. The next thing I need to notice is that in the denominator, when x equals 1 or x equals -1, the denominator becomes 0. So that tells me that I have a vertical asymptote at x equals 1 and x equals -1. All right, so the final thing we need to do is figure out our horizontal asymptote. So we're going to take a look at our chart here. And here's our chart. The highest degree on the top is 1, and the highest degree on the bottom is 2. So using our chart here, I see that n is 1 and m is 2. And I know that 1 is less than 2, so I'm going to choose number 1 as my choice. And that means the x-axis is the horizontal asymptote. And the x-axis is written y equals 0. So that's our horizontal asymptote. All right, and again, you're going to graph it. Just graph it in your calculator. And notice that we had 3 different asymptotes. We had one horizontal asymptote at x equals 0, and you can see when you put it in your graphing calculator that there it is. And we had 2 that were also asymptotes, that they were the horizontal ones, at x equals 1 and x equals -1. All right, here's another one for you to try. Let's do it together first. So the first thing we want to do in this case is factor the numerator. The denominator is already taken care of. So in this one, I see that I have a common 4 that I could factor out. So I end up with just 4 times x minus 3. All right, so now looking at this, I see in the numerator, if x equals positive 3, the numerator becomes 0. So that tells me that my 0 is at 3. All right, and now next I want to look at the denominator, and I note that when x equals 1, the denominator is 0. So that tells me that there is a vertical asymptote at x equals 1. All right, the next thing we need to do is take a look. This time, let's look at our x's here. Notice that my highest degree is 1. There's just a 1 here. And I only have a 1 on this one also. So this time, 1 is equal to 1. So this time I'm going to choose this format. And what I'm going to do is I'm going to take the leading coefficient of the top divided by the leading coefficient of the bottom. So in this case, my leading coefficient is 4 on the top and 1 on the bottom. So that tells me that my asymptote is a horizontal asymptote at 4 over 1, or simply y equals 4. All right, and again, we need to graph that. And when you do, we can see that at y equals 4, we have an asymptote here. And also at x equals 1, we have an asymptote. And when you're graphing these on paper, I want to very clearly see where your x and y asymptotes are, where your vertical and horizontal asymptotes are. Okay, try this one on your own. Turn your video off and give it a try. All right, so taking a look at this one, you should have first factored your numerator. So we're going to look at two numbers that multiply together to get negative 15, add together to get 2. And I know that's going to be a 5 and a 3, and I'll make that 3 negative. So when I factor it out, I have x minus 3 times x plus 5. All right, the next thing I want to see is take a look at the numerator, and I can see that when x equals 3 or x equals 5, the numerator is going to be 0, so that tells me my zeros are going to be at 3 and negative 5. Now, I'm going to look at my denominator, and I can see that when x equals 1, my denominator will be 0. So that tells me that I'm going to have a vertical asymptote at x equals 1. All right, finally, I need to figure out what about my horizontal. So I'm going to look at the degrees of my first terms, my leading terms, and I have a 2 and a 1. And I know that 2 is greater than 1. So I can look at my chart here. And let's see, when 2 is greater, I have it in this order, there are no horizontal asymptotes. All right, so my answer says there's none. All right. And again, we can graph this on your graphing paper. And when you put it in the calculator, you can see that there is no horizontal asymptote, just that one vertical asymptote at x equals 1. All right, here's another one for you to try out on your own. Again, you're going to identify the zeros and the asymptotes. So the first thing we have to do is, there's our handy chart. First thing we have to do is factor the denominator. And so we know that is, we can just factor an x out of that. So we have x over 2, or x minus 2 in the numerator, and x times x plus 1 in the denominator. So taking a look at the numerator, when x equals 2, the numerator is 0. So that tells me that the 0 is at 2. All right, and then the denominator is 0 when x equals negative 1. Or we can't leave out this one when x equals 0. So be really careful that you don't leave one out, all right? So I have 2, so that tells me that our vertical asymptotes at x equals negative 1 and x equals 0. All right, the next thing I need to figure out is my horizontal asymptote. So I'm going to take a look. Notice I have 1 on the top. This is an understood 1, and I have a 2 on the bottom. So 1 is less than 2. So I'm going to look at my chart. I'm going to use this one right here. The x is the then the x-axis is the horizontal asymptote, and that is when y equals 0, or y equals 0. So the degree of n is less than degree of m, so the horizontal asymptote is y equals 0. All right, and then finally you would just need to graph this. So take a look on your graphing calculator and put it in, and notice where all my asymptotes are. Notice I have a horizontal asymptote at y equals 0, and I have two vertical asymptotes, one at x equals 1 and at x equals -1. All right, go ahead and turn your video off and try this one on your own. Okay, on this one, the very first thing you should have done is gone ahead and factored out the numerator and the denominator. And when you did that, you should have come up with this. And the next thing we need to do is look at the numerator. And we see that when x equals 0 or 1/3, that we're going to have a 0 in our numerator. So don't forget that this x is also got to be included in there. So it tells us that our zeros are going to be 0 and 1/3. Next, we're going to take a look at the denominator, and you can see that when x is 3 or -3, we're going to end up with 0. So that tells me that I'm going to have a vertical asymptote at x equals -3 or x equals +3. All right, and then the next thing I need to do is determine what my horizontal asymptote is. So looking up here, I see that my highest degree is 2 and my highest degree is 2. So based on that, I'm going to use this one because they're equal to each other. So now I have to use this little formula. I'm going to have to use the coefficient, which is 3, over the coefficient in the denominator, which is 1. So 3 over 1 is equal to 3. So my horizontal asymptote is going to be at y equals 3. Okay, and you need to be sure and graph this, so put it in your graphing calculator. And when it comes up, you should notice that there's actually a horizontal asymptote at y equals 3. And we have two vertical asymptotes at s equals 3 and x equals -3. All right, in some cases, both the numerator and the denominator of a rational function will equal 0 for a particular value of x. As a result, the function will be undefined at this x value. If this is the case, the graph of the function may have a hole. A hole is an omitted point in the graph. All right, holes in graphs. If a rational function has the same factor x minus b in both the numerator and the denominator, then there is a hole in the graph at the point where x equals b, unless the line x equals b is a vertical asymptote. Okay, so we need to identify the holes in the graph. So the first thing we need to do is factor out the numerator. The denominator is already taken care of. I notice that x squared minus 9 is the difference of perfect squares. So x minus 3, x plus 3. So the expression x minus 3 is a factor of both the numerator and the denominator. All right? So that tells us that there is a hole in the graph at x equals 3. So all we have to do is divide out the common factors. And so actually I have it written in here like this. So when I divide out the common factors, I am just left with f of x equals x plus 3. So this is basically like saying y equals x plus 3. Now the next part of it says we need to graph. So we're going to take y equals x plus 3, and that's a very simple line. It's just a linear. But notice this time we draw a open circle here. That tells us that there is a hole at x equals 3. So at x equals 3, we just come up here, draw an open circle, and that tells us there's a hole there. So the domain of f is x such that x is not equal to 3. So it's everywhere, the domain is everywhere except at this one part where it's x cannot be part of that function. So x is, there's a hole there. All right, try this one on your own really quick. Okay, first thing we do, factor out the numerator. And when we do that, we find two numbers that multiply together to get -6, add together to get 1, And as you see here, the expression x minus 2 is a factor of both the numerator and the denominator. Okay, so that tells us there's going to be a hole in our graph at x equals 2. And we just have to divide out the common factors. And when we do that, we find out that f of x, or y, equals x plus 3. Easy to graph that now. So here's our graph, and we know that there's a hole at x equals 2, so we just draw our line, but then draw a hole there to show there's a hole in our graph. All right, and that's the end of our lesson. It's a little bit long, but I hope you understood it, and we'll talk about this more in class. Have a great day. See you soon. Bye.